So we're going to look at this example now, some thermal expansion of a few bonded tubes. So we've got a couple materials that we're going to work with here. We've got a magnesium alloy and we've got a bronze alloy. Again, the specific alloys chosen because they're at the back of your book. So I grabbed the relevant material properties here. We've got our thermal expansion coefficients, and we got our Young's moduli. So I want to take a tube of bronze and insert it into a tube of magnesium and then bond it with a strong epoxy. So for the bronze, we got an outer diameter of 50 millimeters and an inner diameter of 45 millimeters. And then the magnesium 55 and 50 respectively. So I'm asking here, if we heat it 25 degrees Celsius, A, how much is it going to elongate, and B, what are the axial stresses that would be induced in each material? And I'm also asking to ignore any non-axial strain effects. We're just looking at the elongation and what would occur there. So basically, we've got the temperature that's going to increase, and as that happens, both of them are going to want to expand. The problem is that both of them are going to want to expand at different rates because they have different coefficients of thermal expansion. So if unrestrained, the magnesium would expand this much. I realize I forgot to put the 25 degrees Celsius in there when I was drawing that out. My bad. The thermal strain for the magnesium would be 0.64 micro. No, not millistrain. And the bronze would be 0.425 millistrain, or 425 microstrain, I guess, depending how you want to look at it. Anyhow, so what we know that because they're bonded, we're stuck with the compatibility condition that the strain induced needs to be the same. So due to that, basically, the magnesium, it's going to stretch out to a certain amount, and as it does so, it's going to exert a force that's going to cause the bronze to stretch out a bit more than it would have otherwise, and the bronze is going to do the same. It's going to exert a force that would compress the magnesium a bit so that it only expands a bit less than it would otherwise. And those forces, obviously, need to be equal and opposite. So we've got the forces that are going to be the same, and we've got the strain that's going to be the same. So we can use that to figure out, we can use that to solve for what our strain total is. So the strain total, that's just going to be equal to the thermal strain plus the normal strain. And then it's going to be the same for both. So we start with the thermal strain here for the magnesium alloy, and then we add the stress in the magnesium divided by the Young's modulus, and that's going to be equal to the thermal strain in the bronze plus the stress in the bronze divided by its Young's modulus. And of course, stress can load over area. So based upon the fact that the magnesium is being compressed by the force from the bronze, and the bronze is being stretched out by the force from the magnesium, we put a negative sign here on the load for the magnesium. Put a positive sign here on the load for the bronze. And then, of course, we got their respective areas and their respective Young's moduli. So the area for the magnesium, it's just, the area, the outside diameter minus the area of the inside diameter. So pi over 4 times the diameter squared. And, the outer and inner. So it comes out to 412 millimeters squared for the magnesium. The bronze is obviously going to be a bit less because it's the smaller one. So it's 373 millimeters squared. So we can just plug that in to this equation that we already had, and their respective Young's moduli. So the Young's modulus for the magnesium is 44.7 gigapascals. Young's modulus for the bronze is 103 gigapascals. And of course, just to make sure, I always find that when I'm trying to do gigapascals, it's honestly, when I'm doing my calculations, I almost always just convert it to megapascals, so that I can take advantage of the fact that a millimeter squared times this number of megapascals gives us a certain number of newtons, because a megapascal is a newton per millimeter squared. That seems to be some. It seems to be a method that I like to use to avoid mixing up my units, because obviously you don't want to be mixing up your units. So, anyways, calculating those, we can take our strain value here and subtract from it the strain value on this side. That basically just gives the difference in the strain values. And then on the other side, we can add this term to this side, because again, it's a negative term here, so we add it over. And that'll just works out, once we kind of calculate those out, it works out to P times 1 over 18.4 meganewtons plus 1 over 38.4 meganewtons ends up being equal to 0.0804 P per meganewton. Divide that term over to the other side, and we end up getting that divided by that ends up being 0.00267 meganewtons. Obviously, we can convert that to kilonewtons if we want to have it be a bit more reasonable to work with. So 2.67 kilonewtons is kind of the average force within these bars it takes to maintain the proper, maintain an equal length on them as they expand and contract. So what contraction that actually is? Well, we just need to take the formula that we had for one of those strains and plug in the p-value for it. So I grabbed the one for the bronze, and we just got that value here that we already had, and just take our p-value, throw it into there, and again, keeping like I said, I think it's usually easiest to keep your units straight when you convert your gigapascals to megapascals. So 103,000 times the divided by 2,760. Yeah. So that gets us this value here for our strain. So we can take that, and again, we wanted to find the elongation. So that'll just be the length of the section we're working with. I asked for 1 meter times the strain, which gives us 0.494 millimeters as our strain. And then as for the stress, again, we know the load. We know the load. So we just take that divided by the area. So compression, tension, compression for the magnesium, tension for the bronze, and their respective areas. And we're in the low megapascal range, which, you know, something like this shouldn't be generating forces enough to start getting close to yielding. It's only a 25 degrees Celsius difference, so hopefully that shouldn't be too much of an issue. And that's about it.